first episode of the transformers, and today we're here with our talented machine learning engineer Federica Baldi. She will explain everything about this new technique. Actually, it's not so new because it has been around for a couple of years, probably more. It's really it's really exciting because I think transformers were originally invented and used in natural language processing, but now they're kind of ubiquitously used at Spark. Obviously, we are trying to use them with computer vision, but I think today Federica will also touch base on time series. So we're gonna really look at the transformers at 360 degrees. So without further ado, I would like to ask Federica to start. I'm gonna share your notes here. Again, this is a conversation. Let's make it as as simple as possible. Let's interact a bit. Let's try to really flesh out what are the most interesting point without going too much into the technical details.
Okay, so thank you, Luca. And we will talk about transformers, as you said, because I believe that everyone now knows the word transformers, but not everyone knows actually how they work and what is the intuition behind them. And so we can start from here. So a transformers is a deep learning model that can learn context and meaning through the relationship between the elements in sequential data. How can it perform this thing is through self-attention. That is a set of mathematical techniques that we will explain later. So transformers were first introduced in 2017. As you said before, it's been a couple of years. And they were introduced by a team in Google Brain. And they were first proposed for natural language process tasks like machine translation or language modeling in general. But then they have been used for different tasks in many other areas, such as computer vision and also audio processing and time series. So now they're used almost everywhere, and researchers are still trying to explore and improve this technique to use it in other areas too. So here we have the outline of this episode. So first, we will have a brief introduction of what are transformers and what are the advantages of using them, so why they are so popular. Then we will see the general architecture, and in this section we will dive a little bit into the technical details behind the architecture that was presented in the first paper. Then we will briefly cite some of the most popular models and architectures that are being used today. And we will see the applications, the main applications. Obviously, today is just a gentle introduction. Then maybe in the next episode, we will have the opportunity to go also deeper in the details and the technical details of all these applications. What I wanted to say first was what are the main schemes that we have when we are working with data. So the simplest one is one-to-one. So we have a fixed size input and we want to get a fixed size output. And the classical example here is image classification. So we have our network, we give the network an image of a dog, and we want to receive as output the word dog. This is obviously the simplest task, but then the tasks become more difficult because we have sequences. So for instance, the first scheme is one-to-many. So we have an input that is of fixed size, and the output is instead a sequence that would have variable length. And an example of this scheme is image captioning or annotation. And for instance, we give the network an image, and the network will output a sentence in a language that we know, so in this case, English, that describes the content of that image. Going more complex, we have the opposite case, in which we have as input a sequence that could be a sentence, but also an image we will see later. And as output, we want a single token, let's say, so an output of fixed size. And this is used, for instance, for sentiment analysis. And in this case, we can see that we want to know if the review of the hotel was negative or positive. So we want to infer a single attribute for an entire sentence. And then with the last case, that is the most complex, we have many-to-many. So we have an input of a sequence, that is a sentence, as I said before, or a sequence of elements, and we want a sequence of elements also in output. And the basic example is machine translation, and that was the first task that was solved with transformers. And in this case, we have a sentence in a language as input, and then as output, we want the same sentence, but in another language. And here is the difficulty, because when we have to classify an image, or we have to deal with the one-to-one scheme, we can use the classic feed-forward networks. Instead, when we have to deal with sequences, the things get complicated because a feed-forward network, yes.
And I have a question for you, Federica. If you can go back, just to give our audience the ability to understand the different schemes. Each block there, what is each block? Is a word? Is a piece of sentence? What is it?
It depends on how the network is constructed, but typically each block is a word that is called token. So actually, it is not a word. It's a representation, a vector representation of the word, or a vector representation of a part of an image, of a part of a video, of I don't know, a measure in a time series. This could be anything, but it's a single element inside the sequence.
Okay, and are you going to talk about how to create this representation? Are there guidelines, or it's really open to anyone's suggestions and needs?
It's quite open. Well, actually, for natural language processing, there are guidelines, and there are some embeddings that are widely used, because obviously you do not have to reinvent the wheel every time. So for natural language processing, we have embeddings for most of the languages, but for different tasks, like in computer vision or in time series, this becomes more difficult because there isn't such an embedding. So you need to create it your own, and it can be quite challenging to do so. Also because to do these embeddings, you need a lot of data. So for instance, to create the embeddings for the English language, you need a corpus of text that is huge. So that is why we use pre-trained embeddings, because none of us have the resources, the money also, and time to train these embeddings. But that's it. I don't know if you have any other questions about this.
No, we will explore further questions later, I guess.
Okay, so as I said before, feed-forward neural networks work well for one-to-one schemes, but cannot keep track of sequential data. They do not learn any relationship, because each input is mapped into an output independently. So that is why recurrent neural networks were introduced. So these networks can keep track of the entire sequence. And how they do so, they have this hidden state vector in which they store, this is a memory. We can say it is the memory of the network, because it stores the previous elements in the sequence, and so it learns the sequential data. But unfortunately, this network has two main advantages. And the first one, it is that it's very slow because data is processed sequentially. So for instance, if we want to learn something from a sentence, we need to process each word at a time. So one step at a time. And this obviously does not allow us to work with GPUs, for instance, or with parallel computing that could make this process faster. And the other problem with RNNs is the problem that is called vanishing gradients. I will not go too much into the details here, but the problem is that if for instance, let's say in a sentence or in a text, we have a word, a name, Federica, and then we will refer to the same person in other sentences at the end of the text, so far away from the first time that the person was cited, it's very difficult to track these dependencies. So long dependencies are difficult to track for RNNs. And this is because of the gradients that with back propagation will vanish or explode. And how can we solve this problem? With LSTMs. So this was another architecture that was proposed in order to solve the vanishing gradient problem. And these networks can solve the problem to a certain extent. So for instance, if RNNs can process sequences up to, I don't know, 100 words, LSTMs can go up to 10,000. Still, the problem exists, but the main problem here is that they are even slower than RNNs. So they still process sequentially, and because they are more complex, they require a lot of time for training and for inference. So how can we deal with sequential data, but in a way that's not so prohibitive with transformers? Transformers are able to work with the sequential data, but the sequences are processed in parallel. So we do not process the data sequentially, so each word at a time, but all together. The words can be processed, words in a sentence can be processed all together. Elements in the sequence can be processed all together. And the other main contribution that was made by transformers is this technique that is called attention. That is a technique that allows the network to track the relations between the items also in very long sequences. And we will see how, but these were the main two contributions that transformers made, yes.
Now you're saying that transformers are essentially fixing the problem of LSTM, fact that they are very slow. But you're also saying that you're processing in parallel sequential data. Can you be a little bit more explicit, maybe with an example, so that we understand? Yes. Because the two things are, kind of contradictory. Sequential processing, parallel processing. So how does it work?
So, for instance, let's say we want to process the sentence that I had before. The pen is on the table. Mm-hmm. So if we work with an LSTM or an RNN, we had to first take process that word, then we process pen, then we process is, and we process on, the, and then table. Okay, so you get that this is quite heavy from the computational point of view. When we work with transformers, we can take the whole sentence and give it as an input to the transformer.
Okay, so the RNN would take each word individually. Instead, the transformer takes the whole thing.
Yes, exactly.
Okay, and what does it do with it?
We will see it in a moment.
No spoilers, Luca.
No, yes, because obviously the first thing that comes to your mind is with RNNs, we understand that the following words will know the previous ones, no? So we can see that it's easy to track the relationship because pen knows that before there was the, etc. If we process them all together, how can we do this? And this is performed with attention and another mechanism that I will explain in a bit. So
excellent. Okay.
So let's go back here. So here I will present the general architecture. So this is the architecture that was presented in the first paper. And then, as I said before, transformers are evolving and various architectures are being proposed, but all follow this baseline. I don't know how to say this architecture that was proposed at first. So this is the architecture, as you can see. It is an encoder-decoder structure. So we have two parts. The encoder is the one on the left, and the decoder is the one on the right. If we want to say in a nutshell what is the task of the encoder and what is the task of the decoder, the encoder takes an input sequence and generates a sequence of continuous representations. So in the input sequence, we have discrete tokens. We have the words, as I said before. Mm-hmm. Instead, as output, we generate this continuous representation. So we we change the space in which we are located, okay? Then the decoder takes as input the output of the encoder and also the output of the decoder at the previous step. And then it outputs a final sequence that is the one we are trying to obtain. So for instance, the input is the sentence in English. Then this sentence is transformed into something continuous in a space that we don't know, but the transformers obviously can interpret. And then from this continuous representation and the representation that previously was known by the decoder, we obtain the output sequence that could be a sequence in Italian, from English to Italian, okay? And the most important thing is that we do not rely on recurrence and on convolution. And this is why this model is so quick. And also, if we, it has been proven that if we use sentences or sequences that are very large, the time that it is needed to process them doesn't change. So while RNNs and LSTMs required an incremental amount of time to process more data, transformers can do that in no time. Okay, obviously a little bit more than a single word or a simple sentence, but there's not this incremental I don't know how to say time, okay?
Okay.
And so this thing that we do not rely on recurrence and convolution, as I said before, it's sort of a problem. So how can we capture the information about the relative position of the words? We do that by positional encoding, but first, maybe I will talk about this embedding. We have said that before a little bit, but the thing is that obviously the transformer is a network. So the only thing it can process are numbers, vectors, tensors, okay? So if we have images, if we have sentences, if we have time series, the first thing we need to do is to transform this input into an embedding, that is into a vector representation. Then this can be processed by the transformer. So this is the first step that must be performed. And then we have this positional encoding that is here. And this is the most important thing, because as I said before, since we have no recurrence, no convolution, the information about the relative position or absolute position about the single element in the sequence is injected by this positional encoding. What does this mean? It means that we give a sort of weight to the single token based on its position inside the sequence. here you have an image, and you can understand that based on the position of the token inside the sequence or of the word inside the sentence, you get a different encoding dimension. And this can be done in many different ways, but in the original paper, you had these sine and cosine frequencies. They decided to use that because maybe it was the best for natural language processing at the time, but I know that in different architecture, they use also different positional encodings, okay? So what you can do, maybe this is a quite intricate part, so you
Let
have
me
your
ask.
words. Yes.
Let me ask you one question. So, is this this positional encoding is the mechanism implementing the attention?
No, we have
Not yet.
not yet. We have multi-head attention. I will get to that in a moment. This is prior to the transformer. So the transformer is the one in gray here. This is the previous to that. So
Okay.
it's sort of a pre-processing that you need to do on your data before giving them an input to the actual architecture, okay? But why do you need positional encoding? Let's go back to the sentence of before. Maybe it's easier. So the pen is on the table, okay?
Mm-hmm.
If you use an embedding, one of the ones that are pre-trained, I don't know, there are a lot of them, you get that each of these words is mapped into a vector. So for instance, let's say we have integers, so it's easier. There is 1, 2, 3, 4, 5, and 6, okay? But these vectors, they do not change based on the position of that word inside the sentence. For instance, I could change the whole sentence, I could change the order of the words, but this vector will stay the same. And this works well if you have recurrency, so if you have a recurrent neural network. But in transformers, you need to know where the particular word is positioned. And the positional encoding is sort of multiplying this vector that you have, that is given by the embedding, by a certain value that tells you that that word is in that position. And so you get a context. You know in which context you are using that word. And by the context, you can also learn the relationships between the words. So for instance, if you say the red pen is on the table, by knowing that red is near to pen, you know that that adjective is related to pen and not to table. So it's the pen that is red and not the table, okay? Instead, if you use only embeddings, you cannot retrieve any information about the relationship or the context and the meaning of the words, okay? So I don't know if it was clear, because this is quite complex to explain, but I hope
much clearer. Let's have a look at the that picture that you showed, and let's try to understand
yes.
So how this positional encoding works from a mathematical perspective. So this is a b-dimensional function with some sine and cosine, 2D sine and cosine
Yes.
function. So what you do is you take your vector, your input vector, and then you said you multiply this vector by these weights, the weights that you are deriving from
well,
this.
actually, it is not multiplication. I was wrong. It's actually they add up, so they perform a summation. So they get this original vector that is d-dimensional. They compute the positional encoding that is still d-dimensional, and then these two representations are added up, and we obtain the input to the transformer.
Okay, so the
I said
encoding
wait because it was easier to explain, but it's actually a summation.
So in this example, the encoding dimension is the dimension, the size of the input vector, right? So the embedding vector.
Yes.
And
Yes.
then the position index represents, which is 125 dimensions wide, represents essentially the context, the amplitude of the context, right?
Yes.
So this is an additional matrix. So this, you would add this matrix to your input encoded matrix, okay? And you will then have a reweighted input vector for the transformers.
Yes, perfect. This is the what is happening.
Okay, and how do you parameterize this positional encoding matrix? Do you have any ideas? You just follow,
I believe you can follow the literature, so see how others are doing. There are many methods. There are some methods that are also learnable, so that you can train also this positional encoding. But you can also use these kind of encodings that instead are fixed and decided a priori and not learned by the network. This was the first positional encoding that was proposed. I don't really know what they are using the most now, but I believe we could look it up and see. But yes, I am aware that there exist different methods. This is not the only one. And so, as I said before, we have two parts: the encoder and the decoder, and they share some similarities. I will talk about them separately. So first, we have the encoder, and this consists of a stack of n identical layers. And in the original paper, this n was set up to 6. And each layer is composed of two sublayers. So we have multi-head attention and the fully connected feed-forward network. I will explain what multi-head attention is, but what you have to know is that each sublayer has a residual connection, so that the output goes back into the input, and a normalization layer. So we have that this thing here, it's repeated 6 times, and inside we have two sublayers, multi-head attention and feed forward. Okay. Then I don't know if I can say something else. So these layers are identical, as I said, but the thing is that they obviously do not have the same weights. So it's like in convolutional neural networks, when you apply different kernels to the same layer, they all learn different things, even if they are applied in the same manner. Okay. And the decoder is similar, as I said before. So we have, once again, n identical layers, and this is 6 in the original paper. This time we have 3 sublayers. So the first one is what they called masked multi-attention or multi-head attention. And then we have the two same layers as before. We still have residual connections and normalization layers. But the thing is, what is masked? Okay. The problem here is that when you are decoding, you cannot take into consideration the whole sequence or the whole sentence, because you have to learn what word is coming next. If you already know it, then you are not learning anything. Okay. So for instance, let's say the pen is on the table. Then the first time I learn la, I cannot know penna already. I need to learn that after la goes penna, and then all the subsequent words will only take into consideration the previous ones, cannot know the words that are upcoming, okay? And this is why it is called masked, because we mask, we sort of hide the later part, and we only take into consideration the part that we have already processed. This way, we learn what is coming next, and we learn how to decode the thing that has come, that came as input, okay? But this is foggy, I know, because we don't know what attention is. So we can see it here. Okay, positional encoding is applied also here. You can see, but I have already said that. So attention is something that obviously we know when we talk about cognitive attention, so our attention, because it's when we want to pay attention to our surroundings, to what we have around us. And in neural networks, attention is that mechanism that gives the network the ability to give more importance to some parts of the data and give less importance to other parts, depending on the context. And here I put an example because it's simpler to explain like this. For instance, as I said before, she's eating a green apple. We have that green and apple are strictly related, no? So we have high attention. Instead, for instance, eating and green are not related. So there is a low attention between them. And also eating and apple are highly correlated. So we have high attention, okay? So attention is sort of telling the network, you have to pay attention to these tokens, these other tokens, when you're processing this one. So when you're processing apple, you need to pay attention also to eating and to green. This is what attention tells the network.
In a sense, attention is a mechanism to learn associations or to reweight associations between tokens that are related within a specific context.
Yes.
Is that correct?
Yes. Yes. And how does it work? Okay, does it work? We have these three matrices. We have the Q, key, and V. So Q is the query matrix, and it is the vector representation of one element in the sequence. So the word pen, okay? Here we have its vector representation, obviously added up with its positional encoding. Then we have the matrices of keys, and instead represents all the elements in the sequence. So we have all the sentence. And then with these two matrices, Q and key, we can compute this weight. This time it's a weight because we perform a multiplication. So this attention weight that essentially, it's what I said before, gives more attention, more importance to the tokens in the sentence, in the sequence that are closer to the query, so to the token that we are taking into consideration. Closer in the sense, not only distance, closer physically, let's say, but also closer in context, okay? Closer in meaning. And then what we obtain as output is the V, that is, once again, all the elements in the sequence, multiplied by these weights.
Okay, so let me try to understand this, because this is fascinating. Because it's very simple and it seems super powerful. It is a little bit less simple to understand how it works mathematically. So you essentially take these two matrix, Q and key. Q is is one element in the sequence, which means that it's one token in the sequence. It could be a word or a group of words, while a key contains all the words in the sequence, right?
Yes.
So these two matrices are multiplied not by element, it's a matrix multiplication, right?
It's
So it's
a dot product.
It's a dot product. Okay. So dot product that is scaled by this
This parameter,
vector
yes.
d. We don't know where it comes from, but it's just a rescaling operation. It's about scaling because well, do we have any intuition? Why
Actually,
do
I
we have
read
to
it
scale?
in the paper, but I don't remember why they put that. I can look it up quite easily. I'll go there. There is a reason, obviously, but I don't remember it.
Okay, don't worry. And the important thing is that once we have these values, then the softmax, we know what the softmax does, right? So it activates for certain values. It's a nonlinear activation that for certain values above a certain threshold, it returns a value bigger than zero, or I don't know. Softmax is -1 + 1, right? Or 0 1. It can be
0 1, I believe.
0 1. Okay, so it gets deactivated or activated depending on the values in the matrix. And then once you have this activation, you multiply it by v, by all the values in
V
the
is the same as
sequence.
key. V is the same as key, actually.
Yeah, I can see it. Okay, and so this softmax reweights v and deprioritizes the ones that are not those tokens that are not in the right context, in the current context.
For instance, we said that transformers process all the words or all the elements in the sequence together. So together we have that one time we have Q that is V, then Q is pen, then is, etc. But these are processed together because the information about the context is learned independently. We do not need the sequentiality because we use these softmax that give the relation along with the positional encoding between the position of the word or of the token we are taking into consideration and all the other tokens. Okay.
So this dot product combined with the softmax learns those weak associations between tokens that define the context.
Exactly.
That are context dependent.
And this is a single head, but what we have is a multi-head attention. So we have this repeated several times. So in each layer of attention, we actually have multi-head attention. And this, once again, is done because you learn different representations, so different weights. And all of these weights together give you the network a representation of relevance for the single token inside the context. As I said before, one word could be relevant because it's following another word, but also it could be relevant because of the meaning, because of, I don't know, two words are nouns or one noun with the verb. And with this multi-head, we can learn these relevance relations that are meaningful also to us, to the humans. Okay.
At multiple levels, as you were saying.
Yes.
So
yes.
it could be a semantic level, a syntactical level, whatever. Depends obviously on the features.
We obviously don't know because it is learned by the transformer, but it is proven that it can learn the relations between words that are also distant between. There is a huge distance between them, and it can learn the context and the
And do you have any idea of how many heads typically are used this data parameter to
Also, this
cross-validate?
is
Or
age. In the original paper, age was set to, I have used 64 maybe. No, 8, sorry, 8. In the original was 8. Then 64 is because you have multiple times this repeated. But I believe that this is also a parameter that you have to tune based on the architecture, based on the task, based on what you're trying to solve.
and these are run in parallel and then concatenated together.
Yes.
So these products, these scalar products, sorry, these dot products between matrices are super fast. They are performed in parallel, then they are concatenated, and this is the output for the second
Yes.
the
Then
second
this
part of the feed
it
forward.
goes into the feed forward that is a simple, let's say, neural network. So the ones that we are used to.
Okay, this is clear enough.
And then yes, here I have a little history, let's say, of the architectures that were proposed, because obviously this is a quite complex architecture. So as I said before, we usually use pre-trained models, and there are lots of pre-trained models, depending also on the task. Obviously, most of them are pre-trained for NLP tasks, so they are pre-trained on English corpus or other languages. But there is also something on computer vision and on time series, even if this is quite new in the panorama, let's say. So here we have quite few names. Maybe the most famous one is BERT, that was used to produce text summaries. Then we have GPT-3. This is famous too. That is the successor of GPT-2, and they can perform well on a variety of tasks, actually, and we use them for transfer learning, and I have an example in the next slide. But mainly we have 3 families. So we have Bert, and you can see that there is also Roberta, Albert, Deberta. All of these are part of the same family, and these are called auto-encoding transforming models. Then we have the ones that are GPT-like, and then the ones that are BART or T5 that are it's another family, and they use actually the same exact architecture as I presented before. So the original one, let's say. And an interesting thing that maybe all of us know, have heard, it's Dali, that actually uses GPT-3 that was pre-trained on text, and it was modified to produce images. So what Dali does is it takes as input a caption, a sentence, a description, and it is able to generate images from scratch, images that are realistic and they seem produced by humans. So, for instance, you can tell Dali to produce an astronaut riding a horse in photorealistic style, and then Dali will output this. And this is quite interesting for me, and I believe this is in the news, so everyone has heard about it. But it can also, given an image in a certain style, generate its own creations by varying the original image. So, for instance, this is the famous painting of Klimt, and this is the reproduction that Dali made on its own. So we can understand that actually these transformers are very powerful, and with a structure that it doesn't seem so complex. Well, it is complex, but we can study it and learn it. The transformers can do things that are astonishing from my side. I don't know if it.
Yeah, no, they're incredible. They're incredible, and maybe the next time we can check out
Yes.
what are how Dali works, and how the transformer intuition is declined in to work with pictures, because I imagine
Yes,
there is a
yes.
little bit of tweaking.
Yes, but yeah, here I've listed some applications. So, for instance, NLP, we have machine translations that I've talked about. So we want to translate one sentence in a language to another sentence to the same sentence in another language. Then we have text summarization. So, for instance, we have the text, and we want to extract a summary that has meaning, obviously. So in this case, we need to understand the context, but also being able to generate text. So there is also a generative part. And also in question answering, there's this part of generating the answer to the question. So we must understand the question, but also being able to answer it to it. And there are many others in natural language processing. Then we have computer vision. Here I had an image, but I don't know why it is not showing. Maybe because it was animated. But the thing with vision transformers is that how can we use images as sequential data? Because images are a single input, no? But the thing is that they proposed this architecture in which you take the image and divide it into patches. So you obtain, I don't know how many, but 200 squares or something like that. And you treat each of these squares as a token, so an element in the sequence. And then the transformer can learn by the relationships that there are between the different elements inside the sequence that is our image to, for instance, classify, to detect these objects, or also it is widely used for autonomous driving. So it is what Tesla is using, these vision transformers, to detect where the road is and where are the people in the road. And then also we have an important part on video processing, for instance, for action detection in videos, but also for deep fake detection. So if the video is corrupted or
So they're really widely
fake.
applied across
Yes, also in computer vision.
computer vision.
And then the newest applications are in speech recognition, time series forecasting and classification, actually, and also reinforcement learning. So it is also used. It was recently used a transformer to play chess. So it learned how to play chess, and this is typically a task that is performed in reinforcement learning. So transformers are really very powerful and can be really applied to many applications. The difficult part, obviously, is how to train these transformers, because they need a lot of data. And also, if you are able to understand this embedding, how to create the first embedding before giving it as an input to the network, then the work is done. So, but this is not easy for all the tasks, because in NLP, it's easy.
Yeah.
Each word is a token. For speech recognition, in which we have signals, or time series forecasting, in which we have these continuous still signals are, and this is more complex.
Yeah, and even for time series, right? So what is a token in time
Yes,
series?
it's difficult for time series. It could be the value the single timestamp, but how to embed this value is the real question. So you can have that yesterday the temperature was 30 degrees, and then how can I map this into a vector? This is the most difficult part, and also the one in which researchers are working the most maybe right now, because NLP is state of the
That's
art.
straightforward. Yeah, and it's straightforward embedding.
Mhm.
Let's say
Yes.
even the positional embedding. I imagine that, yeah, I mean, transformers from what you're saying are very tailor made for text, and now they're trying really to stick them pretty much everywhere. Vision, images, I understand. Yeah, I understand that there is a straightforward application, especially in video, for video sequences analysis. I don't know if you are aware of benchmarks and against other approaches, like for instance, we know SoccerNet. We're familiar with that data set.
Actually, the winning team used transformers, so they used a particular embedding that they invented. So they extracted features from the videos with many different pre-trained networks, and they concatenated these features to obtain an embedding, and then use this embedding inside a transformer. But the way this embedding was produced is something that it was invented, so it's quite difficult, and it depends from task to task and from application to application, and this is, I believe, the most difficult part.
So there is a lot of flexibility in the design of the embedding. What about the design of the attention mechanism? Is something standard? Is that multi-head
No.
attention standard, or you can play with it and change it?
You can play with it, and also all of these pre-trained models or architectures that are being proposed propose a different type of attention. So it depends also on the architecture. There are many types. I presented only the first architecture, that was the one that gave birth to the transformers in general. But if you look into all these architectures, they have different fine-tuning of the parameters or of the attention itself. So this is a scale dot product attention. We have other ones.
And in there's also the concept of decoder and encoder. We haven't talked about it much, but there are other models that have the same architecture.
Yes.
Obviously, the autoencoders is one of them.
Also, not all transformers actually use both. So for some applications, researchers have found out. Yes, you just take the encoder, or you just take the decoder, and you use them.
So if you
separately.
want to develop a generative application, you might only use one of them, right?
Yes.
If you want translation, maybe it's just
you maybe
a decoder.
Need it depends on maybe you need both of them for machine translation, because you have to encode the sentence in one language, and from that space that you have generated, you have to decode and obtain the sentence in the other language. So you need both of them.
Super interesting. This is fascinating. Thank you very much, Federica. A great job. I think I even I understood the intuition behind it, the many intuitions behind transformers. Good sign. So next episode, what are we gonna do? Are we gonna look again at the transformers?
Yes, maybe we could see some of this architecture in detail. Maybe if we want to focus on computer vision, we can see the vision transformer, that is quite interesting for us. Or if we want to focus on time series, we can see what are the state-of-the-art models in this field. But for now, I focused on the main concepts, because obviously I couldn't talk about one architecture without giving the background, but in next episodes maybe we can focus us on something. I don't know.
Great. Well, thank you very much. Thanks for watching. And the slides will be available linked in the description below.